welcome to this channel. With this video, I am starting a lecture series on tensor analysis. This is our first video on tensor. In this video, you will learn about introduction part of tensor. So let's start with some examples. So here I am considering some physical quantities. So in the first, I have written temperature, distance and mass. Suppose I am taking temperature equals to 100 degrees Celsius. Distance equals to 10 centimeter, distance between 2 points, right? Let us suppose we have 2 point A and B and distance between these 2 points is 10 centimeter. Suppose we have some object and its mass is 5 kg. So what we write, mass equals to 5 kg. So to represent these terms, these quantities, what we need to represent temperature, what you need a value, a number, right? To represent distance, what we need? 10 centimeter. That means we need a number or a value. To represent mass, what we need? We need a number, or we can say a value or magnitude. So here I considered three quantities: temperature, distance and mass. And to represent these three quantities, what we need? We need only magnitude. And next, I considered displacement and velocity. So I am writing displacement by letter D. So D equals to minus I plus 2j plus 5k. So what are I, j, k? I, j, k are unit vectors or basis vectors along x-axis, y-axis and z-axis. Suppose you have this three-dimensional space. So along x-axis I am taking unit vector or basis vector as I, j and k. So displacement is minus I plus 2j plus 5k. Minus I means we are moving along negative x direction. How much? 1 unit. Minus 1. So minus represent the direction, right? In negative direction. You are moving in negative direction. Okay. 2j, that means we are moving along y axis. How much? Up to 2 units. And along z axis we are moving 5 unit. Okay, so to represent D we need values minus 1, 2, 5. So the magnitude is also associated, along with direction is also associated, right? In the same way, when you represent velocity, you need components, right? I am writing Vx, Vy, Vz. So these are component. So component can take any values, right? So to represent velocity, you need magnitude as well as direction. So displacement and velocity, these physical quantity needs magnitude and direction. Magnitude plus direction. Next, I am writing stress. So what is stress? Stress is force per unit area, or stress is the measure of an external force acting over the cross-sectional area. Okay, so here I am taking some beam. So let us suppose this is beam and O is some internal point in the beam, and we want to calculate stress at point O. Okay, so if you want to calculate stress at point O, so first what you have to do, you have to consider all the cross-sectional areas which pass through point O. Okay, so here I am taking x, y, z. This is our three-dimensional space. So in three-dimensional space, because the beam is 3D figure, right? So in three-dimensional space we have three planes: plane xy, plane xz, plane yz. So xy plane is the plane perpendicular to z axis, right? So xy plane, or we can say z plane, right? So you have three possible plane. Okay, so we have three possible planes. So along xy plane, so if you cut this beam along xy plane, we can cut this plane along xz plane, or we can cut this plane along yz plane. So we have at the end we will have three cross-sectional plane or three cross-sectional surfaces. Okay, so first, this when you cut this beam along xy plane or z plane, okay, so the beam will divide it into two parts. So this is the back part and you will get front part. Okay, so and this is the point O at which we want to find stress. So in the same way you will get this cross sectional area when you cut beam along the YZ plane. YZ plane means X plane. Okay, and when you cut the beam along XZ plane, that means Y plane, then you will get this cross section area. So you want to find out stress at point O, that means we will find stress at point O along this plane, along this cross sectional area, and along this cross sectional area. So in total we have 3 cross sectional area. So first, so at O we will have some stress, right? And we can divide stress in 3 component, because in 3-dimensional space we have 3 axes. So along 3 axes we will have 3 component. So let us suppose we have stress component along X direction, along Y direction, and along Z direction. I am denoting stress by letter sigma. Okay, usually we denote stress by sigma, or in some books you can find tau, right? Here we are writing by sigma. So this is stress on the Z plane. Okay, Z plane we are taking. So what I will write, sigma Z. So this is along the X direction, so I will write sigma ZX. So sigma ZX is the component of stress on the Z plane along the X axis. So first subscript tells you about the cross sectional area, okay, along which you are finding the cross sectional area. So this is the plane of action, okay, and the second subscript is along axis, along which axis the force or the stress is directed, right? This the vertical one, so it will denote sigma. Again the plane is same, sigma Z, but the direction is along Y, and this is sigma ZZ, right? So these three components are the stress component over the Z plane, right? In the same way we can find over the X plane. So here also we will have 3 components, but here the plane is X plane. So what you will have, sigma XX, sigma XY, and sigma XZ. In the same way here the plane is Y plane, so the 3 component will be sigma YX, sigma YY, and sigma YZ. So in total how many components we have? 9 components. Okay, so I am combining all these 3 cross sectional area into one, and I am considering this figure. Okay, so this is Z plane, this is X plane, and this is Y plane, right? So so Tx, what I am writing, Tx is the, what is Tx? Tx is stress along X plane. This is Ty is stress along Y plane. So stress along, so suppose this the green vector, okay, this is Ty. So we can, this green arrow is Ty. So we can divide this Ty into 3 components. So we will have these 3 components. In the same way we have Tz, right? So Tx, Ty, Tz, what are these? These are Tx, Ty, Tz are stresses on X plane, on Y plane, and on Z plane, and further we can divide all 3 into 3 components, right? Now the question arises is that if you look at sigma XX and sigma YX and sigma ZX, okay, so all these 3 components are in the same direction, right? All 3 have same direction along the x-axis. So you might think that can we combine these 3? That means can we add these 3? Okay, in total we have 9 component, but if you add these 3 and combine it into one component, okay, in the same way along y-axis we have 3 components. So if we add these 3 into one component, along Z we have 3 component. If we add these 3 into one component, so we will have 3 components, right? So the question is that can we add these 3 components or not? So here we cannot add these 3 components. Why? Because the sigma xx, this stress component is act on x plane and it is perpendicular or normal to the x plane, right? This is normal. So this stress component is called normal stress. What is called normal stress? And here this sigma yx is acting along the surface, along the plane. It is parallel to plane. So this stress, this kind of stress, what we call, this is called shear stress. And so sigma yx and sigma xx, the direction is same, but we cannot combine them. Why so? Because the nature of force is different. Here this is shear stress, so the force nature is, it will drag, right? And here in normal stress, the force nature is pulling. Okay, so you cannot combine these two stresses. So we cannot combine these three forces, right? These three forces are acting in the same direction, still we cannot combine them. That's why you will have different 9 components. Okay, so I am writing these 9 components in the form of matrix. So for in the first row, what I am writing, all the components which act on the x plane or stress acting on plane yz, right? In the same way, these are the component on the y plane or the plane perpendicular to y axis, and this is on the plane z or on the plane xy, right? Here I am writing x, y, z. So x denotes, so all these components act in the x axis. These component, the direction is along the y axis, and all 3 component has the direction along the z axis, right? So now if you look back, then here in the first part we have considered temperature, distance, mass. To represent these 3 quantities, what we need only magnitude. Then we consider displacement and velocity. To represent these quantities, we need 2 things, magnitude and direction. Now at the end, what we consider? Stress. So to represent stress, what you need? We need magnitude, right? The sigma xx, sigma yz, the components value, that is magnitude, direction, and the other thing is that plane of action, right? So here stress has magnitude, direction and plane of action. If some physical quantities has only magnitude, then what you will say? Scalar. If some physical quantities has magnitude and direction, you will say vector. But here for the stress, what you are getting? Stress has magnitude, direction and plane of action, right? That means stress is more than vector. It is not a vector, but it is more than vector. Now let us discuss the definition of scalar, vectors and then tensors. So what is a scalar? A scalar is a quantity that has magnitude but no direction. Okay, it has magnitude but no direction. For example, temperature, mass, speed, time, distance. And to represent all these quantities, what you need? You need a single number, a single value, right? So how many components associated? Only one component. So it has only one component. The second term is vector. So vectors are mathematical objects that have both magnitude and direction. And the important thing is that they follow the vector law of addition, triangle law of addition. If you have 2 vectors, suppose u and v, then their addition will be this. This will be u plus v. Okay, this is called vector law of addition. So this is very important. Okay, the quantity is if the quantity is vector, that means it has to follow the vector law of addition. If it has magnitude, direction, but it is not following the vector law of addition, then it cannot be a vector. Here I am writing some example, electric current. So electric current, suppose current is flowing in this direction, along this direction, and suppose 5 ampere current is flowing in this direction. So we will say, okay, electric current has some direction and it has value, so it will be vector quantity. But electric current is not a vector quantity. Why? Because it does not follow the vector law of addition. Suppose 5 ampere current is flowing in this direction and 2 ampere current is flowing in this direction, right? And here we have some junction. So how much we will get the current? 7 ampere, right? At junction we will have 7 ampere current. But according to vector law of addition, if you have some vector of length 5 and in the opposite direction you have some vector of length 2, then the resultant vector will have length 3, not 7, right? So electric current does not follow vector law of addition, so it is not a vector quantity. Got it? One more thing is that I have added here means area is a scalar or vector. So area is a scalar quantity, right? But area vector is a vector quantity. What is area? The difference between area and area vector is that area is basically, if you have, suppose this is the closed curve, and the area of this closed curve is suppose 5 meters square. So only magnitude is associated, so area is a scalar quantity. This is okay. So what is area vector? So area vector is a vector which is perpendicular to this area. So we are defining a vector which is perpendicular to this area. So the direction is normal to the area, and what is the magnitude? We are associating magnitude to this vector is equal to the area. Okay, the area is the value of area is the magnitude of this vector. Okay, so area vector is basically we are defining this vector by using the area. Okay, so area and area vector are two different things. Area is a scalar quantity, but area vector is a vector quantity, and area vector has direction is normal to the area and the magnitude is equal to the area. Okay, so why we are studying scalar and vector in the part of tensor? Because scalar and vector are also special case of tensor. That's why we are covering scalars and vectors here. The third thing is tensor. So what is tensor? So tensor has magnitude, direction, it can have plane of application or plane of action, right? For example, stress tensor, electromagnetic tensor. Now next thing is rank of tensor. So what is rank? So rank or order is the amount of information we need to find a specific component. So what is the meaning of amount of information? So amount of information means number of basis vector. So here what I have written, number of basis vector needed to fully specify a component of tensor. That means to specify a component, how many basis vector you need. For example, I am considering here some vector. Okay, this is vector. So here how many components we have? We have 3 components. One component along the x direction, one component along the y direction, one component along the z direction. So to represent every component, how many basis vector you need? So here if I consider standard basis, so I will need this basis vector. For y direction I will need this basis vector, and for third component we need this basis vector. So to represent each component we need one basis vector. So what is the rank of vector? Rank will be number of basis vector. So here what is the number? 1. Okay, so 1 is the rank of vector. So number of basis vector to specify a component, each component. Okay, so to specify each component we need one vector, so rank is 1. That means vector is a tensor of rank 1. So you have studied that vector is a tensor of rank 1. Got it? Now if we consider scalar, so for example scalar, okay, so scalar, let us take example of mass. So mass equals to, let us take 5 kg. So to represent this, how many basis vectors you need? So 5, this is complete. Okay, this is complete information. We don't need any basis vector. Okay, So 5 kg, so 5, this because only value is associated, there is no direction, no action of plane, so we need no basis vector. So how many basis vector you need? We need 0 basis vector to represent a scalar. How many basis vector? 0 basis vector. So scalar is rank 0 tensor. Okay, so what is scalar? Scalar is rank 0 tensor, vector is rank 1 tensor. Okay, so basically scalar and vectors are also tensor of rank 0 and 1. So here I have written tensor of rank 0 is scalar, tensor of rank 1 is vector. Now tensor of rank 2. So tensor of rank 2 is also called dyad. And in example I am writing stress tensor. So why stress tensor is tensor of rank 2? So let's move back here. Okay, so this is stress tensor. Stress tensor has 9 component, right? And we have represented stress tensor in the form of matrix. So let us take this component. Okay, so we have 9 component, and to find rank we need to find the basis vector. Okay, so to represent this particular component, how many basis vector or how much information you need? So here sigma xx, that means, and the first subscript is for the plane of action and the second subscript is for the axis, okay, along which axis the force is acting. So here two information you need. The first is along the area and the second one is along the axis. So two information or two basis vector you need. Okay, so stress tensor, so for each component how much you need? Two basis vector we need. So stress tensor is a tensor of rank 2. Okay, electromagnetic tensor, we will see electromagnetic tensor in the further slide. So these two examples, these two are example of tensor of rank 2, and tensor of rank 2 is also called dyad. In this way we can define tensor of rank 3, and tensor of rank 3 is called triad. Now vector, what is vector? So basically vector, so let me take some example of vector 1, 2 and minus 3. I can represent this as I plus 2j minus 3k. Okay, and 1, 2, minus 3 are the component. Okay, so we write vector in the form of column matrix, right? So basically if you look at each component, so what are the component? These are scalars. So basically vector is collection of scalar, right? It is collection of scalar. Okay, so tensor of rank 1, what is tensor of rank 1? Is collection of tensor of rank 0. So if you have collection of rank 0 tensor, you will get rank 1 tensor. Okay, tensor of rank 2, so we have stress tensor, and we denote stress tensor, we have written stress tensor in the form of matrix, right? So what is this matrix? Basically matrix is collection of column vectors, right? So tensor of rank 2 is collection of tensor of rank 1. So if you collect tensor of rank 2, you will get tensor of rank 3. If you collect tensor of rank 3, you will get tensor of rank 4. If you get tensor of rank 4, then you will get higher order, higher rank tensor, right? So to find tensor of rank 3, what you need? You have to collect tensor of rank 2, and we denote tensor, or we write tensor of rank 2 by using matrix. So here this triad means tensor of rank 3. Okay, so so we are collecting matrices. So if you collect matrices, so what you will get? You will get tensor of rank 3 or triad. Here we are considering 3-dimensional space, so I am taking 3 matrices. If you are considering n-dimensional space, then you can collect more than 3, right? So now how we can calculate number of components, right? So if you have n-dimensional space and tensor of rank m, Okay, so how many component will it have? So the number of components will be n to the power m. What is n? N is the dimension, so dimension to the power rank, right? So scalar, okay, if you are considering three-dimensional space, so scalar has how many component? So scalar is rank 0 tensor, so 3 to the power 0 1, and we have already seen that scalar has one component. For vector, so vector is tensor of rank 1, so it will have component 3 to the power 1, 3 components, and we have seen that vector has 3 components. So this is the general formula to find the components of tensor. For tensor, so if you consider, so I have considered here two tensor, stress tensor and electromagnetic tensor. So stress tensor is tensor of rank 2 and dimension 3. Okay, dimension is 3. So how many component? Dimension to the power rank 9. And electromagnetic tensor is an example of tensor of rank 2 but dimension 4. For electromagnetic tensor, how many dimension we have? 4. So the number of component will be 4 square, that is 16. That's why 4 by 4 matrix is considered. Okay. So this is formal definition of tensor. A tensor is a physical quantity which remains invariant under the change of coordinate system and obeys certain transformation laws. That means if you are changing from one coordinate system to other coordinate system, then the physical quantity, the value of quantity will not change, but its component can change. Okay, and it will follow certain transformation laws. So in the next video we will discuss about transformation laws of tensor. Okay, if you find this video helpful, then please like it. If you are new to this channel, then please subscribe this channel. Thanks for watching.